Good afternoon, everybody. A couple of procedural items first. I got an email from the people that organize those Edge courses that say that on the streaming video, some of the material that I show here is not readable. I mean, that doesn't apply to me in particular, but that was a general procedure. I cannot do much about this type of material, but the presentations, I would ask either people that are outside campus or people that are on campus and prefer to watch the streaming video to call my attention to places where the font size wasn't enough so that they couldn't follow it. So give me feedback. I usually don't cram too much into a slide, so I don't think that this is a problem, but if it is, let me know. I put in a new homework assignment, but it's sort of a mini one. It basically, if you go to the homework section, let's see. You'll see that I ask you to revisit two of the problems that you did for the first homework. The first one, you are basically asked to use the shadow prices. This is the platform problem in order to predict what would be the effect of increasing the strength of each one of the cable. And that's meant to be individually, so I'm going to end the word individually. That is, you're not supposed to scale them all by 25% because that part, you don't need to be a genius to tell that what will happen is the load carrying capacity will go up by 25%. So instead, this question is basically intended to ask if we have the option of buying more expensive materials for one of those cables, and that material is 25% stronger than the present material, which one should we invest in? For the problem 3 in the same chapter, I want you to exercise what we'll cover today, which is something called the Pareto front, or the trade-off between two objectives. And so I added another objective, which is to minimize the difference, the relative difference between the two areas that you optimize presently in this problem. That is, on the one hand, you want to have minimum weight, and on the other hand, you want to have not to have too big a discrepancy between the two cross-sectional areas that you use. So this is those procedural matters, and now we can go back and look at today's material. Oops. Didn't connect it. Let me see if there is an easy way for me to remember. Otherwise, I'll be reduced to using the board, but that's not a good solution. Optimization. Okay, well, let's engage in a bit of guessing game. Maybe I'll give it a few tries and see if I can remember the name of the file. The name of the directory, okay. So this was the intro. And now I have to come up with a name that includes multi-objective. So let me first write that. Yeah, that's a pity because this was there yesterday mid-afternoon, and the whole idea of putting it there early so that you have it and you can print it and be able to make notes on it. But so this is a response to a request by two of the class members asking that we do multi-objective optimization. And we are going to do it in 2 installments. The first installment is this one. We just intended to acquaint you with the notion of multi-objective optimization without paying too much attention to different computational strategies. Then when we get to discuss genetic algorithms, I'm probably going to ask one of my graduate students, Tushar Goel. Before he came here, he did a master's degree on calculating the solutions to multi-objective optimization problem by genetic algorithm. And that paper that he wrote as a result of his master's thesis was apparently so good that he told me that there are only 56 references to that paper that he published in 2001. Many of you are not familiar, that number 56 doesn't make maybe too much of an impression. So let me say that most of the professors in this department don't have a paper with 56 references, 2 or more. So it's a very substantial contribution, and that partially happened because he did his master's degree with Professor Deb from Indian Institute of Technology, who is the world expert on doing multi-objective optimization with genetic algorithms. So I'll probably let him tell you about it. But right now, we want to do the basics. And the basics is that, as you saw in the fun problem, it's very common that we have more than one objective. And that means that when you compare 2 design points, you cannot simply say that one is better than the other. That is, when you have only a single objective, then every time you compare 2 points, you can say this is a better design than the other. With 2 objectives, you cannot always do that, or most of the time you cannot do that, unless you are comparing 2 points where all of the objectives are poorer in one point compared to the other. And if you have this situation, you call those points that are poorer than other points on all the objectives dominated. So one point can be dominated by another, or one point can be dominated by a set. Could anybody care to guess if somebody gives us a set of points that we already visited, and we give one new point, and we say this new point is dominated by the set, what could it possibly mean? So again, when two points are compared, one point is dominated by the other if it's clearly inferior. That is, all the objectives are poorer. So if somebody gives us 10 points, let's say that those 10 points are not dominated by one another. That is, you cannot find a point among those 10 that can be tossed out because there is a clearly better point in the set. So all of those 10 points, each one of them has an objective which is better, or combination of objectives that are better. And now we add point number 11. Yes?
So, just as an example, what Shama, are you talking about like in the fun example where you had two different things that you could do to earn money, occupy your time and stuff? So you're saying that you couldn't differentiate between the two of them. You couldn't obviously say, oh yeah, the fourth one's much better than the third one. We can just throw the third one out. That's what you're saying?
Right. So yeah, that's I think that I have this example on. Okay, so this is not a complete example because of the fact that we don't want a pay of 1, 2, or 3. We want a pay of 100. So how to compare the points is not clear, but for example, we can take item 1 and say, in order to meet the pay requirement, we need 100 of those, and then we are going to have 300 minutes and 300 fun. For point 2, we will need 50 of those, so we will require 200 minutes of times, and we'll get a fun of 100. So when you compare 1 and 2, they don't dominate each other because 1 is better on the fun and 2 is better on the time. You will go to point 3, and point 3 requires 100, and it has a time of 200 and the fun of 200. And so what can you say about it? I mean, you may want to write those numbers if you cannot keep them in your head like me. That is point 2 dominated by any of the other points or not?
Or 3 dominates. Yeah, 3 dominates 1.
Yes, that is, we can now, well, no, we are getting less fun from 3 compared to 1. But when we compare 3 to 2, the time required is the same 200 minutes, but the fun that we get from 3 is 200, and the fun that we get with 2 is only 100. So 3 dominates 2. Okay, let's look at 4. For 4, we need 33 minutes, and we are going to get a time of 66 and a fun of 33. Is it dominated by any of the points before? Or does it dominate any of the points before? So we can say that point 1, 2, and 4 are a set of points that is not dominated. That is, we cannot throw away any of those points. We will say that point 3 is dominated by the set of those other 3 points. What do we mean by that?
If you have 1, 2, and 4, you would never pick 3.
Right. So a point is dominated by the set if we can find a point in the set that dominates it. So what we will be doing in the process of doing multi-objective optimization is we'll be in the process of collecting points that cannot be dominated, and we'll call them all optimal. That is, there is no way to choose amongst them. And then, if we are just the optimizers and there is a person who is doing the real design, you'll present him with all of those points and ask him which one he likes best. That is, he basically told us, I want to minimize my time, I want to maximize my fun. Here is a set of points that do that. You choose. So, the concept is old, and it doesn't have anything to do with engineering. Yes?
Does it mean that you would have to have a preference for one of your objectives?
Not you. Maybe the designer would have a preference, or maybe he will look at the data and discover a preference that he never knew about before. It turns out that that's actually the scenario which is most likely to happen in my experience. One of the most difficult problems that you have, turns out, is to take a physical problem and convert it into mathematics. That is, what we do here is shield you from this harsh reality. That is, in practically every course that you take at a university, the process of taking the physical problem and converting into a mathematical one is semi-trivial, and we concentrate entirely on how to solve the mathematical problem. When you do optimization, oftentimes the challenge is to formulate the optimization problem, and oftentimes you do a poor job. So you go and optimize the problem, and then you present it to your customer, and he says, no, 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 that's no good at all. And you ask why, and he said, yeah, obviously. You know, you cannot have something with such a ridiculously low x1. And you say, why? And he said, yeah, because of this. Oh, you never told me that this was a constraint. Or you give him those points, and he says, oh, obviously this is a much better than design than the other. And you say, why? And he says, isn't it obvious that it should be this or like that? And you discover that there is some aspect of the objective function that he thought was obvious, or he never thought about of telling you, or he discovered it at the moment. That is, he never thought about it because he never had to face it. So this is what optimization problems do to you. That is, so sometimes you don't need to agonize. You have a physical problem, you formulate it. If you didn't formulate it right, the optimizer is going to reveal it to you very clearly. That is, it's basically going to solve the problem that you ask it to solve instead of the problem that you want to solve. So you get a solution and you say, oh, that's not what I wanted. So the person that invented this idea of multi-objective optimization was an economist. And if you think about it, this makes sense because you don't need to have engineering to have conflicting objectives. What are the kind of objectives that economists typically considers? Well, I mean, but
What kind of objectives?
objectives.
Money,
I'm sorry? Production. Okay, so, but if you think about objectives that have conflict among them, you know, a company, you could say they don't really care about how much they produce. What they care is the bottom line. So could you give me a situation where there is a conflict, that is, there is another objective, clear objective, that even if you don't care about the ecology or, you know, don't bring in confusing aspect, but just from the standpoint of a cold-hearted economist, what would be the most common conflicting objective to the bottom line? No? I mean, you are a cold-hearted economist. You are just interested in making money. I'm sorry? Time, okay. So if we factor that out by saying my objective is to make the best profit per month, so that we eliminated time.
With the fixed production, you want to have, you want to give products at cheaper price, and you want to
No, you don't care if you can sell people. You see, maybe you are not at the age where this is an issue, but maybe you have parents or relatives or friends that do that. People invest money and they want to get profits or to get nice investment return. What is the other object? Which classical conflict you have in that scenario?
How much money you invest versus how much money you keep.
Let's say that you have $100,000 and you can invest it in government bonds, in the stock market, in real estate. You have all of those investment avenues, and your one objective is to make as much money as possible. What would be the other competing objective?
not lose it by risk.
Okay, so risk versus return. Okay, this is the typical economic scenario. You can buy government bonds. You have, on average, you have low return, almost zero risk. Instead, you can buy some racy hedge fund, and maybe on average you do better, but there is a substantial risk. So this is the kind of so Vilfredo Pareto, as you can see from the name, was an Italian, and he lived, most of his productive life was in the late 19th century and early 20th century. And as far as I remember, his paper on multi-objective optimization was published in 1904. So he wasn't that young, I guess 56 at the time. And the general equilibrium theory that he developed doesn't have anything to do with multi-objective optimization, but it has to do with the fact that an economy can be in equilibrium. For example, right now, we are not in equilibrium with respect to gas prices. They go up. It may take 6 months for people to adjust their driving habits, and then we will reach another equilibrium. But that equilibrium is not purely economical. It's affected also by some preferences and tastes, and that's where the multi-objective optimization comes in. So he dominates the terminology. Multi-objective optimization is usually called a Pareto optimization. From time to time, people will add the word of Edgeworth, which was, I believe, a British economist that also did something along that line. So some people will say Pareto Edgeworth optimization, but almost everybody just calls it Pareto optimization. I got this information by Googling the guy. So when I copied it, his picture didn't come through. But if you are interested, this is the first entry, if I remember, on Google when you type in Pareto optimization. So this is the example that you take, and I said that the fund can vary between 33.3 and 150. So I now we'll go about formulating the multi-objective problem. We want to minimize time and maximize fun. And I lost one constraint. That is, before I had a constraint of 150 on the fun. I still have the other constraints. But the question is, how do I solve this problem? And before I show you how do I solve it, here is how it looks. What I did here is I generated a large number of combinations of x1, x2, x3, x4. Remember that this is the number of items or number of activities that I engage in. And I got all of these points in the function space. This is called the function space. That is, I'm not showing it to you in the x1, x2, x3, x4. I'm showing you what combination of time and fun I got. This is not by solving the optimization problem, but just trying different combination of x1, x2, x3, x4, provided that they satisfy the constraint. That is, all of those points that you see here satisfy the constraints. How do we say satisfy the constraints in a single word? It's a synonym of doable. Feasible. Good. So all of those points are feasible. They are in the feasible design space. And obviously, those black points that you see here dominate all of those points, at least up to here. I didn't try to continue beyond 300. But if you take the points up to here, all of the blue points are dominated by the black points. That is, so if we take, for example, a point here that has 200 times 200 minutes and 100 units of fun, there is no point to settle for it. We can go horizontally and get the black point here that gets the same fun for about 120 minutes, or we can go vertically and get 200 and fun for the same expenditure of time, or we can go diagonally and get some other better combination. So the blue points represent different choices of what activities to engage in. The points on the black front, which is called the Pareto front, so Pareto optimization front is abbreviated as POF. Is this an acronym, by the way? Yeah, that is POF. I can pronounce it two ways, POF and POF. Now, only one of those would be an acronym. Which one? POF. Otherwise, it's technically an initialization or initialism, but most people still call it an acronym. But technically, there is a difference if you pronounce it as a single word. So I've never heard anybody call it POF. So technically, it's not an acronym. Anyhow, this is the front. So the question is, I can do it the hard way. I can simply, in this case, I generated, if I remember right, about 10,000 points. Maybe only 2,000. I kept. It took a long time for Matlab to do that, so I kept chopping. increasing the interval between points, and I'm not sure where I ended. But you can do it this hard way, that is, in this case, trying takes a microsecond, so it's not a big issue. But if you are designing a structure and each point requires a finite element analysis that takes 2 hours, then it's going to be very expensive to generate the front by doing all of the blue points. How can we generate only the black points? Can anybody think about how we can do that?
Fix one of the fixed time and then optimize only for fun.
Right. So this is indeed the preferred way, and this is how I generated it. That is, the problem that we did last time is we fixed the fun at a minimum of 150, and minimized the time. So I then repeated it for different values of the minimum required fun, and I'm guaranteed that, if I fix the fun at 150 and minimize the time, that it's going to push me to the left, and I'm going to end up on the curve. The other thing that is probably not apparent, does anybody see that the black line is not a straight line? Okay. Could anybody tell me where the break is? About 200 times, yeah. Does anybody have an idea of why we would have breaks like that?
Change of the variable. It's using a different variable, different point.
Well, each one of those points correspond to different combination of x2, x3, x4.
Or you're butting up against a different constraint?
Yeah, so actually, if we go back to the data, we need between 33.3 to 100 items to make $100. And even if we use the most let me see. Okay, maybe it's not obvious what it will be, but at a certain point, if we want a lot of fun, the time may stop being, the money may stop being a constraint. So this is where the break is. At that point, we are completely controlled by the fun constraint. Okay, so this is what it is. And now for a bit more mathematical terminology. So normally we can have not only 2 objective functions, we can have more than 2. So let's say M. We have a design vector x star. We will consistently use the asterisk to denote the point where the minimum is achieved. And this is another bit of jargon. The mathematician will call x star the minimizer. Okay, this is not something that engineers would normally do, but when you read the paper that was written by a mathematician and you see the word minimizer, this is a shorthand for the vector of design variables which minimizes the objective function. So x star is a Pareto optimal if and only if there is no vector x in the feasible space with the characteristic that it's better than x star on all the objectives, or at least as good and strictly better on one of them. Because if that's the case, that is, if it wasn't worse than x star for all of them and it's strictly better on another one, then it will dominate, x will dominate x star, and x star will not be, will be a dominated point, and therefore it's not Pareto optimal. Any question about this mathematical definition?
So it just means the point x is at least as good for all points except for one, which is, or x star is at least as good, if not better, for all points except for one, which is definitely better.
Right. But we say it in the opposite. You cannot find a point in the set that would do that to x star. Okay, so there are two classes of solution methods for Pareto optimization problems. They basically divided into methods that try to avoid generating the Pareto front and methods that ask, okay, we have to generate the Pareto front here. What is the best way of doing it? So 100 years ago, definitely, but even 20 years ago, or even 10 or 15 years ago, almost everybody did this first class of method that basically said, let's try and guess which point on the Pareto front is going to be best when the customer is going to look at it. And they would invent different rationales for how the customer will look at the Pareto front and decide which points they like best. And most of those methods are based on first generated the Utopia point. And let me show you what the Utopia point would be for the fun problem. The Utopia point is the point that represents the best combination of those two objectives. So in this problem, the best time is 33.3, the best time is 66 about, and the best fun is 450. So a Utopia point will be somewhere here. That is, we will have 450 units of fun with 33, oh, no, the other way around. Here. That is, we'll get 450 units of fun for 66 minutes of work. Now, when you consider the black points here, this method would say, I like the point which is closest in one sense to this Utopia point. So this is there are different combinations of that, and when you look at those different ways of avoiding doing the Pareto front, you'll discover that some are disguised pretty well so that you don't see this rationale that clearly, but essentially most of them boil down to this. And the reason that this is dangerous is, first of all, as I told you, when a designer looks at designs, he often discovers things about their preferences that they didn't know before or didn't verbalize before. And so this is also, yeah. I think that's all that I want to say about that. So let's look at the method that generates the Pareto front. The most common way that people use, because it appeals to the notion of weighting your objectives, is to say, I'm going to weight one objective from 0 to 100%, and the other objective to 100% minus what I weight the first objective. So I'm going to do optimization with, let's say, 0.1 times the first objective plus 0.9 times the other objective, and so on. You cannot do that when one of them is minimized and the other one is maximized, because you won't know whether to minimize or maximize that combination. So you first convert them both to minimization problem, and then you take the weighted sum. Turns out that that works for most cases, but there are cases where the Pareto front is non-convex, and you see that the issue of convexity comes in again, where that can miss some places on the Pareto front. The most sure method is to optimize one objective for a range of constraints on the others, which is what you indicated you would do. And then when you have a population-based optimization method, that is, instead of just optimizing with one point or another, there are methods that are called niching method, which again try to imitate the market. You can have 100 people that all want to minimize risk and maximize profit, but each one of them does something else because they find a different niche. And these population-based algorithms try to, essentially what they add, they say they add another objective to the optimization by each one of the members of the population. I want to be as far away as possible from the others. And this helps in getting the entire Pareto front. So this is what I used to do the problem, that is minimize time such that the pay is at least 100 and such that the fun is equal or larger than a series of k's. And here is the Matlab segment that I wanted to show you because it's important that everybody gets into the habit of using fmin_con. This is the function, the Matlab function that we will use more than anything else this semester. And so this is the initial design. When you do Matlab fmin_con, it wants you to tell it where to start. Then here is the range of funds that I took. Start with 30, go in increment of 5 up to 300. The lower bound on the x's are 4 zeros. The thing which is nice about Matlab is that when you call a function routine, you can call it with all kind of customizing, and fmin_con, along with a few other, takes advantage of option function called optimSet that you can specify different conditions, and you may want to look up doing help optim set and see what they are. And then this is one of the ways you can call f-min con. In this particular case, on the right side, I'm telling it which function will calculate the objective function, what's the initial guess. I'm telling it that I have a series of linear constraints where the matrix of the constraint is A and the right-hand side is B. I am giving it the lower bound. I'm skipping some, including the upper bounds, and I tell it that I've changed the options. Notice what I've done with the A and B. Could anybody tell me where did I get those numbers in A and B? Yeah, but I've done one more thing. Yeah, that is I multiplied by -1 because as I told you, the convention is more and more that that's the way constraints are specified. And then this is the objective function, which is the time that I want to minimize. So, any questions? The one last thing that I want to do is to go back to the homework problem and make sure that everybody understands what the two objective functions are. Okay. Let's see if I can increase the font size. Doesn't help much. Okay. So in problem 3, you design a truss, and obviously in order for it to be efficient, it will pick up different cross-sectional areas for the two areas that you have there. The other objective function is the difference between the areas, and so we want to minimize weight on the one hand, and we want to minimize the difference between the areas on the other hand. And so can you see how you can get the utopia point here? That is, the utopia point would be the answer, what is the best objective function if I care only about one objective function, and what's the best objective function if I care only about the other? So you have already found what is the best weight if you don't care about the difference between them. What is the easiest way to find out what is the design if you don't care about the weight, but the only thing that you care about is about the fact that they are the same? Right. You just make it a single variable instead of two. So in this, and it's important that you do that so that when you get the other results, you have something to compare it to. Now, the constraint that the two areas, I mean, the fact that we want the two areas to be as close to each other as possible, you will be tempted to express it as a ratio. And that will destroy the linearity of the problem. And so think about how to do it while still doing the problem in a linear way. You don't have to. F-min con will solve also nonlinear problem. It's just that its fidelity, that is, it gets often stuck when you ask it to do nonlinear problems, while it is much more foolproof when you ask it to do linear problems. So you have an incentive to try and solve this problem while still doing only linear programming. Any questions? Okay, this will be all then. You have a good Labor Day weekend.